And it wasn't that hard to get started. You just had to add a simple modem that they called a terminal unit back then. But it was a very inefficient way of sending information. You flip on your transmitter, it's sitting there transmitting solid carrier, 100%, and it would just send one character when you pressed a key. There was no error checking. And it used a 5-bit code commonly called baudot. And of course, 5 bits is not enough for all the letters, numbers, and characters. So 2 of the codes were reserved for shifting between letters and other figures. And very often you'd shift into the wrong state, and then what should be letters would be numbers and characters. But it was amazing to see the mechanical beast print out those characters. So in the late 1970s, some hams in Canada started experimenting with an entirely new way of sending information over the radio. So rather than sending one character at a time, information would be saved up and sent in a small short transmission called a packet. And each transmission contains some framing information, address of where it's going to, where it came from, and information. And it had error checking, so you'd know if it got through correctly or not. So this is how you would do packet radio in the old days. You'd have typically you'd have a dumb terminal, or maybe a terminal program on a computer. You'd have a device in the middle called a terminal node controller, which is just a modem and a microcontroller with some brains, a microcontroller that knows about the protocol, and a radio. So there's many advantages. Rather than having your transmitter on 100% duty cycle, you just send short bursts. Each packet contains information on where it's going to and from. So this allows many people to share the same channel at the same time. There's error detection, so you know if it was corrupted in flight. And the connected mode would do acknowledgments and automatic retries to attempt to get the message through, even if it failed the first few times. And of course, you had digital repeaters. Oh, and another important thing, it was completely transparent, so you could send any sort of arbitrary data. For example, you could send a JPEG image file, not just text. So the Vancouver group made their design available just as a bare printed circuit board. So it was a lot of work to gather up all the other components. So it never really gained too much popularity. And American hams were really held back on this because the FCC didn't allow ASCII to be used over ham radio until 1980. So hams that wanted to duplicate what the Canadians were doing had to get special permission. So packet radio really took off when the Tucson Amateur Packet Radio Association, or Tucson Amateur Packet Radio, came out with their TNC1 kit in 1983. Okay, they threw a lot of hardware at it. One time I counted 27 integrated circuits in there, which just seems kind of crazy. It was complete, all parts, everything, including modem, power supply. It was $350 without the case. The documentation was 2 inches thick, and they even had their a custom binder made with Tapper printed on it. This was also available from Heathkit as the HD4040. And a couple years later, they came out with the TNC2, which is a lot smaller and cheaper. And the design was licensed to MFJ and other manufacturers, and then things really took off.
John, do you remember the prices of any of these items at the time?
This kit, I'm pretty sure, was $350. I still have one up in my attic. I really couldn't tell you what a TNC2 cost. I know it had to be considerably cheaper because they made it a lot smaller and more, many fewer parts. I think around like late 90s, I bought a Cantronics KPC3 Plus, and I'm pretty sure it's just about $200. Okay, so let's see, where were we? We were talking about Tapper. Okay. Okay, so the TNC was initially designed for a person to be sitting there with a dumb terminal. And from there, you could monitor what was going on. You could connect to another station. You could talk to other people. But when people started connecting TNCs up to computer applications like bulletin board systems, it became very clear that this was not a good interface for the TNC2 application, because characters going to the TNC could be either commands for the TNC, or they could be data to be transmitted. In the other direction, text coming from the TNC could be just monitoring of what's happening, like on the first line. It could be echoing of commands. It could be status changes. It could be data from another station. So it can be hard to sort that all out. So, for example, if the text that you received said **** disconnected from somebody, your application would think, oh, you're disconnected. So that would like really confuse it. So, 1996, I think it was KA9Q came up with this idea for a keep it simple, stupid protocol. And now the TNC can have a much smaller brain because it doesn't have to know about all the protocol. All it needs to do is handle the framing. So the computer application formats the data exactly as it would go over the air, and then TNC just adds the framing on the ends and the checksum, or the checksum, whatever. Of course, this was one of those things where it was a quick hack meant to be temporary until something better came along. But here we are, many, many years later, and we're still using it.
35 years.
So, packet radio was real hot stuff for a little while. And, it seemed like every week someone else came out with a new TNC design. And then the 1990s struck. We all had internet access and lost interest in setting up bulletin boards on ham radio. So what do we do with all those TNCs that no one wants anymore? Well, WB4APR came up with a scheme called APRS, or Automatic Packet Reporting System. And I just want to emphasize that it's not a vehicle tracking system. In fact, the inventor of the system said it was something like a tactical real-time information source for local situation awareness. So APRS has a lot of potential, and most of us are only a small part of it. But this is not a presentation on APRS. It's about getting rid of the old TNCs. So, up to 20 years ago, this is the accepted way of doing things. You'd have your computer program. The computer talks to a TNC over an RS-232 cable, and you have your radio. But you don't need special hardware for modes like FT8 or PSK31. So what makes people think you need special hardware for APRS? You can do it better and cheaper just using software. This approach gives you a tremendous amount of flexibility, because you're no longer constrained by that RS-232 cable. So you could have, like I do, you could have a Raspberry Pi running the TNC software in your shack. It could be running a digipeater and an IGate. You can connect it up to a weather station. It can have multiple radios. And then you could be, in nice weather, you could be sitting outside next to the swimming pool with your laptop, and then you can connect to the virtual TNC using Wi-Fi. So, I mean, lots of stuff you can do here. Okay, so the software I'm talking about tonight is called Direwolf. It's a free open source software replacement for the traditional TNCs. It's very portable, runs on Windows, Linux, including Raspberry Pi, Macintosh, and BSD. Without adding any additional software, it can use a GPS tracker, digipeater, internet gateway, and an APRStt gateway. And it can be, while it's doing all of that at the same time, it can be used as a TNC for all of the popular APRS applications. And all the modern applications are capable of talking to an old TNC through a serial port, but they all understand KISS protocol over Ethernet, TCP/IP, so it could be Ethernet or Wi-Fi. You might be wondering where the name come from. I thought something like soft TNC was like really lame. So I started juggling different words around to try to come up with an acronym, and this is what I came up with.
Well, I like that Linux is in it.
Yeah. Yeah, I don't know how to squeeze Mac OS X in there. But that was a later thing. So this is a block diagram of all the functionality. Don't try to read all the words, because I'll get back to many of these. The important thing to notice here is the layering. So on the bottom we have our radios, either traditional radios or SDR. On the bottom we have modems and other ways of generating sound. And then above the middle line, we have different things that produce packets or consume them. So that's better. Everyone else is muted. So over on the right here, we have our little map, so you can see what we're talking about. We need some way of getting audio in and out of the computer. This is an old-fashioned sound card from before the time when it was standard equipment in the motherboard. But even though the physical shape has changed, that terminology is still used. This is like a USB audio adapter that runs in the $5 to $10 range. If you look closely, you'll see a couple wires sticking out of here. The reason for that is because many of the very popular chips used in these devices have leftover general purpose I/O pins. So the software can use those, well, in my case, to activate the push to talk. The Signal Link USB, I think everyone has one of these, is basically an overgrown version of the USB audio adapter, but it has isolation transformers to keep the RF out of your computer. And finally, this is a board that fits right on top of a Raspberry Pi. It's called the UDRC. It has a connector here, which matches the 6-pin connectors found on many radios. And there's a newer version of this called DRAWS, which has 2 radio connectors, built-in GPS, a regulator so everything can run from 12 volts. I think it has a real-time clock and A to D and other stuff. Software-defined radio can also be used, and there's different ways of getting the audio from the SDR software into Direwolf. So here's something very interesting. The protocol used for packet radio and for APRS is called AX.25. It stands for the amateur version of X.25, which is a commercial standard. And it says absolutely nothing about the modem to be used. But in practice, just about everyone uses a Bell 202-like modem. And the reason for this is because one of the Canadian groups happened to get their hands on a big pile of old Bell 202 modems for 75 cents each. So that's what they used, just as a quick and dirty temporary method of getting something up and running quickly. But of course, anything quick and dirty and temporary usually turns out to be permanent. So we're still using that like more than 40 years later. In the late 1980s, there were several different designs to send 9,600 bits per second. I don't know if I'd call them modems because they just shoved the digital signal directly into the radio. The important thing to remember if you want to use higher speed is that it will not work with the microphone and speaker because of the audio filtering and limited bandwidth. Many radios have a 6-pin mini DIN connector, which is usually labeled data, but it's not data, it's really audio, and it bypasses the normal microphone and speaker filtering. So you have wide bandwidth and very flat, up to about 5 kilohertz. Okay, Direwolf also has a Dtmf, commonly known as touch tone decoder, and it also generates tones. And internally, this is right here. Internally, it's stored in the same form as any other packet. So applications can process incoming touchtone sequences or cause them to be transmitted. And we'll get to an example later of where this can be used. Okay, there are dozens of free speech synthesizer applications available. You just feed in text and out comes spoken words. When the destination for the packet contains speech, it runs a user-defined script which can then invoke a speech synthesizer. So if you wanted to, you could send out a beacon periodically, put destination speech, and then the information part, whatever you put there, will be transmitted as synthesized voice. And it can send Morse code too, just for fun. So here above the second line, we have different things that either produce packets or consume them. Beacons are automatic periodic transmissions, and if these could be locations, a car or a house or whatever. If the location comes from a GPS receiver, then you have a tracker. Custom beacons, well, okay. Custom beacons of any sort of user-defined content that you want to put in them. And some people use this for broadcasting weather reports.
I've seen people use it to show like a repeater's amplifier temperature.
Yeah, that would come under, oh, what a coincidence, telemetry. Okay. Yeah. So APRS has a special telemetry format that allows you to specify labels, units, units, and the actual data. And the Direwolf contains a telemetry toolkit, which contains building blocks for your own applications. There's even a complete example in there where an analog converter is hooked up to a Raspberry Pi, and then it transmits the voltage measured from that. Okay. So very few hams of portable equipment for APRS, but almost everyone has a handheld radio that can send touch tones. So APRStt is a method that allows somebody who only has a radio with touch tone generation capability to enter information into the APRS system. And this idea has been around for about 20 years, but never became real popular because the earlier implementations required specialized hardware, and they weren't very adaptable to new situations. So here's an example of where it could be used. Supposing the organizers of a canoe race wanted to keep track of the locations of all the participants in a race, but they didn't have the budget to put a GPS tracker in each canoe. So what you could do instead is you could put observers at various points along the way. And the APRStt gateway is then programmed to recognize sequences of 3 digits. The first digit represents a predefined location, and the other 2 digits represent an object number. So the observer at checkpoint 3 could punch into the radio 312 pound when canoe 12 is going by. And the gateway would then acknowledge receipt of this by saying canoe 12 is at checkpoint 3. It would also convert this into an APRS object and then transmit it in normal APRS form. So people could then see the updated location of each of the canoes on a map. Okay, digipeater is short for digital repeater, right? You already have one, I think, from the earlier discussion. Most people know what this is. So it has the same function as a voice repeater. It just extends your range by retransmitting signals. But unlike a voice repeater that listens on one frequency and simultaneously transmits on another, this is usually on a single frequency. It receives the packet, looks at it, decides if it's eligible for being repeated, and if so, it retransmits it. This is known as store and forward. Okay, so the purpose of an internet gateway or IGate station is to enable the flow of information between disjoint local radio networks. And it should really be two-way for the full functionality to work. Some people think that IGate stations exist just so that you can view the worldwide APRS activity on a web browser, but they're really missing the big picture. That's only one use case. It's meant to be a two-way system, and receive-only IGate stations break the system, and I'll get to an example on that. So this shows how APRS can be used to send a message to somebody on the other side of the world. So here we have ham1 in Waltham, who sends a message to ham2, which could be anywhere in the world. It gets picked up by the local gateway station, goes over the network, goes to the servers, and then the servers say, where have I heard ham2 recently? And it says, oh, I heard ham2 on gateway B. So it sends the message to gateway B, that goes over the radio, and ham2, who could be on the other side of the world, receives the message. The messaging software automatically sends back an acknowledgement to the origin. So the sending station knows if the message has been received or not. If it doesn't get an acknowledgement in a certain amount of time, it sends it again, until it gets an acknowledgement or exceeds a retry count, and then it'll tell the user that delivery was on it, delivery failed. So if you had, supposing this gateway station was receive only, where it took from the radio to the internet, the message would get to the destination, but when the acknowledgement comes back, it stops here. So that breaks the system. And that's why receive only IGate stations are bad. Two-way IGate stations, could have legal problems in some countries, but they're fine here.
Yeah, and that is our part of the goal with taking advantage of the fact that we've got high-speed internet at the site now, is to be a two-way IGate, full functionality.
That's great, because that's the way the system is supposed to work. Let's see, where are we? Okay, application interfaces. So, while Direwolf is acting as a digipeater and IGate and all this other stuff all at the same time, it can also be used as a TNC for applications. So as I was saying before, I have the software running on a Raspberry Pi up in the attic where it gets hot in the summer and cold in the winter. And I could just be in some other part of the house or outside next to the pool, and I can access it over Wi-Fi and run my applications there. Now there's two different interfaces here. We've talked about KISS, which is really, really simple. The application says, here, transmit this, or on the receiving direction, pretty much we just verify that the frame check sequence is good, and then we pass it on to the application. There's no brains in here. There's another interface called the Agw Network Interface that came from the Agw packet engine, and this exposes a lot more intelligence in the TNC, specifically the link layer that gives you connected mode. And unlike the old RS-230 cable that allowed you to connect one thing, you can connect a whole bunch of applications all at the same time. My favorite topic. So I have no academic or professional background in digital signal processing, so I had absolutely no clue on how to go about building a modem and software. So I did a lot of reading, a lot of experimenting, relentless tweaking until I got something to work. This is what a typical signal looks like. I think this is like actually off the air because it's not perfect. We have two different tones, 1200 and 2200 hertz. We're sending 1200 bits a second. So the modem just has to say, well, which tone do I have? Do I have this higher tone, one logic level, or do I have this other tone? And it doesn't have a whole lot of time to figure this out, because right here, this is 1200 hertz, and this is 1 bit time. This is one way that you can do it. There's other ways. But what I do is I have a bandpass filter for each one of the tones, and then it detects the amplitude, and it goes through a low-pass filter to let the data part through while blocking out the audio tone. And then we just compare which one's greater, and that gives us a 1 or 0. This goes into something called an HDLC decoder, and that looks for that special pattern of 0, 1, 1, 1, 1, 1, 1, 0 at the beginning and end, and then it checks for the frame. Well, it checks for the proper CRC to know if it was received correctly or not. So I was able to get something to work with perfect signals, but I was very disappointed when I tried it on the radio, and it really didn't work too well compared to a traditional TNC. So what I really needed to do more tweaking was a collection of real-world signals. WA8LMF to the rescue. So he lives in Los Angeles, and one day he went driving around during rush hour, recording actual APRS signals. Okay, the frequency was completely saturated. There was under deviation, over deviation, people stepping on each other, and there's a lot of weird stuff in there. And I found it so interesting. I wrote up a complete document with some of the stuff I saw in there. At the bottom of the document is called A Closer Look at the TNC Test CD. So you can find that in the Direwolf documentation. So track one, okay, this is available for free for download. So you just download a file and you can burn an actual CD. So the first track has flat audio from the discriminator of a receiver. And then track two later had post-processing in hopes, well, the idea was to make it mimic the typical receiver behavior for what would come out of the speaker. He didn't do it exactly right, but it's still valuable. And this has become the de facto standard for measuring demodulator performance. A lot of people have measured different TNCs with this test CD. And here I've gathered together all the reported results that I've been able to find. Don't take it too seriously, because this was done by different people, different times, different conditions. But you know, when I did see different people reporting on the same device, they were generally about the same. So what we see here is the ones in yellow are software TNCs, and the white ones are the more traditional TNCs with modem chips. And there's a pattern here which becomes clearer when we make a little graph. So we see that the modem chips do pretty well. You know, from the 700s to upper 900s packets received. The early software was pretty bad. And so this is where the a tarnished reputation came from. And you'll still see articles out there where people say that software TNCs are no good. You need to buy the hardware. That might have been true 20 years ago, but the situation's now different now. The two top TNCs, Direwolf and the UZ7HO sound modem, outperform any of the modem chips. Okay, now this is a big part of our problem. When using modems, you would like the audio coming out of the receiver to be exactly the same as the audio going into the transmitter, because any sort of distortion is going to make it harder to demodulate or decode the signal. And we saw earlier that some transceivers have a special socket to bypass the audio processing, so you can get flat audio. Now, FM voice transceivers have something called preemphasis. And what that does is it boosts the amplitude of the higher frequencies. And then on the receiving end, the receiver has a low-pass filter to reduce the amplitude of the higher frequencies. This is supposed to reduce noise. And it might be good for voice, but it's really, really bad for modems. So here's an example of what happens when we have a mismatch of the technique used for transmitting and receiving. So in this case, the transmitter transmits flat audio. That is, it does not do preemphasis, but the receiver has the de-emphasis. So here, the higher frequencies are substantially smaller in amplitude. And here we have the opposite case. where someone uses the microphone input of the transmitter, and the higher frequencies are boosted in amplitude, but then the receiver has flat audio. So there's the lower frequencies, and then when we have higher frequencies, the amplitude gets bigger. So, I mean, this this works sort of, well, I'm trying to find the right words. This decreases the ability of the modem to decode the system or decode the signal properly. It works reasonably well, but it's not optimal. So my first attempt to work around this problem was to add automatic gain control to the amplitudes of the two tones that are decoded. And that worked a little better, but the AGC just wasn't exactly right. I couldn't get I'm running out of words here. It was improved, but the AGC really didn't work the desired way all the time. The noise would throw it off, and it was better, but just not that great. So this is a brute force way that you could use to solve the problem. You could have 3 different demodulators, and then in front of one, you put a filter to decrease the higher frequency, and on another one, you have a filter to increase the amplitude of the higher frequencies. And then over here, we just eliminate the duplicates that occur very close to each other. I used a variation on this theme because this part is very computationally intensive, hundreds of multiplies and adds for each audio sample going through. So what I did is increased or decreased the amplitude of one of these before doing the compare. And this requires less compute power, and it still works very well. And this works real well. All of the modern software TNCs use something along this theme, where they have multiple decoders that run in parallel, and then it removes duplicates that pop out at pretty much the same time. Okay, last topic. So what can you do if your signal's just a little too weak? It gets through partially, but not reliably. Well, you could increase power. You could get a better antenna. You could move to higher ground, but those aren't always options. One common technique is to add redundant information to the signal so that the receiving end can still get the entire message, even if part of it is lost during transmission. This is a very common technique. It's used like everywhere for radio communications, QR codes, and I mean it's even used on audio CDs and DVDs, so that even if there's a scratch, you can still read it perfectly. There's redundant information in there, so the missing part can be recreated. So
I believe that came out of PARC, didn't it? I think that was a Palo Alto Research Center thing.
PARC?
Yeah.
What?
Yeah, the CD parody piece, or how they did that.
Yeah, Red Book Audio uses that. I know.
Yeah, I don't know the details of exactly what's used on a CD, but they do use some sort of forward error correction. So 19, or not 19, I forget what century it is. In 2006, the StenSat group came up with a very clever scheme to add forward error correction to AX25 and still maintain compatibility to existing equipment. So what they did is, first, they would send a carefully constructed 64-bit pattern that they call a correlation tag. And this is very carefully constructed so that even if you shift it 1 bit, 2 bits, 3 bits, you're not going to get any false matches. Then they send the original normal AX.25 frame. This includes the beginning and ending flag patterns, bit stuffing. I didn't talk about bit stuffing. And the frame check sequence. And after that, they send some parity bytes. And this uses Reed-Solomon encoding, which actually was developed at MIT some years back, a long time back. So depending on the size of your AX25 packet and the number of check bytes that you want to add, there are a number of different correlation tags that specify how many data bytes follow and how many check bytes follow. Now, their application was for amateur radio satellites. So all of the existing applications for receiving this were oriented toward receiving signals from satellites. So I thought it would be interesting to implement this in a general purpose TNC, and that would open up the possibilities for other places that it could be used. So this shows the improvement for normal or for APRS, where we just send independent packets. What I did is I set up a test case where I'd send 1,000 packets. And then on the receiving end, bit errors were artificially introduced with a certain probability. So of course, when there's no errors, it all works perfectly. When we get to a bit error rate of 1 out of 1,000, only about half of the packets get through. And when there's an error rate of about 1 out of 100, it's completely useless. But with the FX25, it just keeps on going, no errors at all. I mean, after the regular AX25 is completely useless. I also tried it for the old traditional connected mode packet. In this case, I sent 100 lines of 128 characters each. And of course, you remember that the connected mode, in the connected mode, the TNC automatically does acknowledgments and retries if it doesn't get through. So with no errors, okay, and this is the throughput. I took the total number of bytes and divided by the time. So with no errors, it moves right along at a certain rate. as the error rate increases, there's more retries. So it slows down and eventually reaches the point where it just gives up because there's too many retries. Now with the FX25, the maximum throughput is considerably smaller because there's more overhead, but it just keeps going. Just keeps going, no degradation at all after the AX25 is completely useless. So, I guess in conclusion, I just want to say again that there's no shortage of packet radio and APRS tutorials on the internet. Unfortunately, most of them are like 15 or 20 years old or even older. Most of the guides that tell you how to get started insist you need to spend $200 on a box that was designed in the 1980s. If software TNCs are mentioned at all, it says that they're no good. But times have changed. There are now multiple software TNCs that give you better performance, more features, and at lower cost than the traditional TNCs. And that's it.
All right.
Any questions? Comments?
Yeah, so I have a couple of questions. One I had was, does your advanced decoder mean that we can just hook up Motorola Max Track, which is doing pre-emphasis, de-emphasis, whatever, right? Or, what should we target as? What do you find people are targeting as a radio for this?
Okay, let's see, what are people using as radios? I mean, anything. I mean, some people have old commercial radios they've repurposed. I mean, most probably use ordinary transceivers. I've even seen people use these little SA818 modules that are use the same chip used in the Baofeng radios.
So the hope was like if we can improve on things by having the flat receive and flat transmit, that would be great if that helps things. But
for receive, I put a lot of work into Direwolf, so it would work in both cases. But it is better to have flat receive because once you have the de-emphasis, you're really adding more distortion to the signal. And and as well, finish this topic. But for transmit, do you want to use pre-emphasis or flat? I don't know, because some people use one, some people use the other. My gut says you want to use flat because you're not distorting the signal. But most people are probably taking audio from their speakers, so they use de-emphasis. So it's a lose-lose situation. Okay, go ahead.
Elliot had a question.
Yeah, I think I just finally figured out why you weren't hearing me earlier. I had the wrong audio selection. Yeah, first of all, congratulations on getting such performance out of a computer, even a Windows computer. I helped set up Echolink on our Waltham 2-meter repeater, and I can tell you that as much as we like Echolink, its software touchtone decoder was horrible. It bounced. If you typed 1, 2, 3, it would come up 1, 2, 2, 2, 3, 3. So we use we actually have a hardware interface. So I'm curious. I understood the basics of your block diagram, but on something like Windows, which is not really a real-time operating system, how do you code that so you can be decoding these tones in real time? I understand you optimized that last slide showed how you optimize and reduce some of your number crunching, but it's still a lot of number crunching, isn't it?
Yeah, I mean, your typical, well, let's see. My development machine is a Windows computer that's like 10 years old, and that still decodes the signals something like 30 times real time. So, I mean, that can keep up just fine.
Wow, what language do you write your code in?
It's in C.
Okay, thank you.
In old C. And I'm using a Raspberry Pi Model 1 for digipeater IGate, and that's more than adequate.
Thank you. That's pretty cool.
Yeah, this is a little. Oh. This is a Model 1 that has like a DAC hat on it, but it's an old. That's an old Model 1. But that's pretty cool if you're able to do it with that, because that's pretty low powered, processor.
Yep. John, the software is all available. It looks like right there in that top link, the github.com. Is that correct? Yep. Where you obtain the software?
Yep.
Perfect.
Yep. That's the source code. You download it, and there's instructions on how to compile it. There's a pre-built version for Windows, because Windows users are not in the habit of building software from source.
Well, there's that Windows subsystem for Linux thing or whatever now, I guess. Yeah, well, that's cool.
Mm-hmm.
John, a question. What do you think about the Moby Link D?
I know somebody who has one. I don't have direct experience, but I mean, that looks like a fairly handy little gadget. You strap it on the side of your radio, and then it talks to your tablet through Bluetooth. I really couldn't tell you what the decode performance is.
Okay, yeah. I mean, I know it's open source software and all that, but I was just wondering if you knew what the genesis of that software was.
No.
Are you able to just explain a little bit about how it works when we're bi-directional with the internet, and like how it's determined that we're the people to transmit a packet out from the internet? How does that happen without blasting everybody all over the place?
Okay, you mean for like messaging, like this slide?
Sure, yeah, so that we're able to support that idea of messaging coming, via the internet to us, and then us relaying that out to the Boston area.
Okay.
Like what prevents us and 50 other people from transmitting that all at the same time, or is that what happens?
I think it is possible for multiple IGates to transmit, because this guy might be he might be between two IGate stations, but he might be moving around. So I don't know this for a fact, but I believe that the server sent it to all the IGates who heard it recently.
Yeah, I believe you set a mileage limit on each node when you set them up. I think you tell it, I want a 20-mile range or a 30-mile range. I believe there's a parameter you can set in there for distance, but I think a lot of nodes get the signal. They just like to avoid data collisions, they each have a separate random number time delay they do before they retransmit, obviously. So if you're in the same radio zone, and again, I haven't set this up or successfully, I should say, myself, but I know for trying to get the data up to like other sites, you actually have to have a login to like, Google Fi or whatever to upload the data for like the APRS parameters, so the node gets populated into like, websites and so forth, that type of thing. So your node, you actually have to get credentialed to be able to post that data up, if that makes sense.
Yeah, well, it's security by obscurity.
Yeah, exactly.
In order for the IGate station to feed information into the servers, you have to log in. Typically, you'd use the call sign, and then you have to give it a passcode, which is derived from the call sign. And in theory, people who set up IGates are supposed to contact the IGate software to obtain this code, but the secret is out. I'm sure you could figure it out in 2 minutes.
It's just a hash. There's nothing more than that.
Yeah, I think it's just a hash. Yeah.
And if you use any library, you can generate that hash by yourself. I mean, there is not a secret. And to answer Ron's question, if you are between two IGates, you basically, like I think it's Ned said that the IGate, they don't, basically there is a random delay, and also there is a delay between each retransmission. So if your radio gets a message from IGate A, for example, the radio should transmit an acknowledgement. So the acknowledgement will be received by the IGate B, in the best case, and the IGate B will know that it doesn't need to send that packet because the acknowledgement has been received.
Okay, thanks for that.
Okay, yeah. When the IGate station logs in, they call it filter. I would call it a subscription. You specify the types of information that you want. For example, you can say, send me, I don't know, all position reports within this certain radius, or send me everything, give me everything transmitted by some certain station. There's a whole bunch of different they call it filters. By default, if you don't do anything at all, the servers will send you messages, and I put messages in air quotation marks because that is the special meaning for APRS. It's a message is addressed to a specific station or a bulletin. By default, messages for anyone heard in your area get sent to the IGate, but you can ask for additional things. That makes sense? So if you just use all the defaults, you're all set in most cases. But let's suppose one of your friends was traveling cross country. What you could do is use the buddy filter and say, send me everything that came from station named such and such. And then the servers would send anything from that particular station here, and then it would get transmitted locally. So there's it gets kind of complicated. The default, okay, if you just take all the defaults, messaging works, and that's I think that's the main value for the two-way IGates. But you can configure them to obtain other information.
Yeah, the only time you got to be careful, I think, is if you're close to like another digipeater or something like that, where you can create a lot of noise traffic. So they tend to not want you to do that. So you might have to strike down your distance or something like that. That's one thing I kind of saw in my sniffing for information on how to set it up. But I'm sure defaults work great for most folks.
I guess, yeah, if you have a really good spot for transmitting, do you want to set your number of, you set the number of hops for it or repeats, so you wouldn't want that super high if you've got, because you just go, because that's the issue with weather balloons, isn't it? Right? They don't configure them right, and then they
blast. They blast it everywhere.
Yeah. That's a good point. As part of the IGate configuration for packets, that come from the servers to the IGate, when you transmit, you can configure it for the maximum number of digipeater hops that they will take. I mean, if you have a really, really good location, you probably want to set that to 0, because if you have really good coverage, there's no point in having all the home stations repeat it, because they don't have much range.
Okay. Yeah, I think that helps. All right. Well, I don't know if anyone has any other questions, but we are running pretty late, so I want to go ahead and at least wrap up the official part of the presentation. So I'm going to go ahead. If there's no more questions, I'll stop the recording. Did Elliot, you have one more question? Were you waving? Or?
No, I just wanted to say thanks to John. That was really informative. Very, very well done.
Yeah, it's great.
Does the website have a listing of equipment that you need to get this on the air?
A computer and a radio? That's